Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode Comedy 1277. Count square submatrices with all ones. This question has been asked in Google, Meta, Amazon and a lot of good companies. It is a typical big dynamic programming based problem, but I will try to discuss all the different approaches to solve this problem and how I solved it. This problem is marked as medium. Let's have a look at the problem statement. We are given m cross n matrix of ones and 0. So it is clear that this matrix can have either the value equal to 1 or 0. Only two type of values are there. Return how many square submatrices have all ones. How many square submatrices where all the elements are only 1. Constraints are saying that the length will go till 300, row 300, column 300, and the values can either be 0 or 1. So this is our problem statement, that this matrix is given. In this matrix, count the number of submatrices where all the elements are 1. So if I try to see, this is one submatrix where all the items are 1. This is another submatrix, and this matrix should also be square submatrices where sides are equal. If it is 2, it should also be 2. This is also 1, 3 cross 3. So starting with this one, if I say, okay, let me clear it. If I say, if I'm checking against this value, let's keep it as a left top corner of the matrix. This is one matrix, and this is another square submatrix. This is another square submatrix. So this item, this number is contributing 3 to our answer. So initially, if my answer is 0, this value is contributing 0, this value is contributing 3, and this item is contributing 1 square submatrix, 2 square submatrix, 2. So 3 plus 2, and so on. And starting with every single item, we need to check how many submatrices I can form. So this is my problem statement, that in this matrix, count the number of square submatrices. That's all. And the matrix is going to have values either 0 or 1. So let me give you some idea that how I solve this problem. Because when I read this problem statement, it reminded me of something which is range sum query in 2D immutable. That problem. And that problem is a typical prefix based problem. Prefix sum based problem. That problem is that starting from this to this, what is the sum of this square? It reminded me that problem. And why that problem is related to this problem? If let's say I am checking the sum of this portion, this left top portion to right bottom portion, if this sum is equal to 4, right? In that case, I can say that this is a square. This is a square where all the items are 1. If let's say I'm checking a square of 2 size, 2 length 2 and height 2, then that is a square of all 1 if the area or sum of all the items are equal to 4, which is length into height, this into this, both the sides. So that is why I came up with that approach, and when I tried solving it using prefix sum, it got submitted successfully. Why? Because first of all, I created prefix of this grid, and then using that prefix, what I checked is what is the longest, what is the biggest square I can form from every single item. What I'm saying is that n square into n time complexity I took to solve that question, and that got submitted successfully because the constraints were not that strict. Later on, I tried to solve it using backtracking, which is the typical approach to solve this problem. And let me give you a quick idea on how I solved it using prefix sum. So later on, we'll just start with our dynamic programming approach. Let's take the same grid if I'm taking the same grid, it is something like this: 0 1 1 1 1 1 1 0 1 1. And using this grid, what I did is I took prefix of this grid. And what is the prefix? Prefix means for every ij starting from 0, 0 till I and j, what is the sum of all the items? That will be called the prefix of this grid. So prefix ending here is sum of all the items in this block. And how do I check that prefix? For that, let's say if I have to check prefix of this block. Okay, this block we need to check the prefix. To check the prefix of this block, if I see what is the prefix of this block, that will be having sum of all the items like this. If I check the prefix of this block, let me mark it circle. If I mark the circle on this one, and if I check the prefix sum of this item, that item will be having sum of all the items like this. And what is the prefix of this item, this one, circled in black? This one. This one is equal to, let's say this is my I and j. If I try to derive the formula, the prefix of I and j is equal to the yellow portion. What is this yellow portion? Prefix of I minus 1 and prefix of j. Okay. And prefix of this green portion. Green portion is prefix of I and prefix of j minus 1. Okay. Now yellow portion I have added and green portion I have added. But here you might wonder that, okay, this portion is added twice. If this portion is added twice, what is this portion? This portion is the prefix of this one. And this is prefix of I minus 1 and prefix of j minus 1. This is added twice, so that's why I have to subtract it from the equation. Now I have all the portion where this yellow portion and green portion and the common portion is included, except the actual value at this value, this index. So what is the actual value? Whatever is my matrix I and j. So that is my actual value. See, this is something, this equation is something you need to understand. And this equation is a part of range sum query question. Range sum query question for 2D, and it is immutable. Immutable question is one which you have to see. Immutable means the grid is not getting changed for every single query. This question is something like, we will be given a grid, and in that grid, starting with ij to I1, j1, whatever is that square having the sum, just written that sum. And to do that in O1 time, O1 per query, we were using prefix sum. Prefix sum. So this is something I have not taken in detail. Why? Because I assume that if you are solving a DP problem, you must have done the prefix sum properly. And still, if you are facing some difficulties, do let me know in the comment section or ask me the question. Or the second thing is, do check out this one. This is like a bonus approach that I'm explaining to you. And this is the formula. And after this formula, I will be able to have the prefix of this grid. So this grid is 0 1 1 1 1 1 1 1 0 1 1 1. Okay, this is the grid. And what is the prefix of this grid? The prefix for this grid will be equal to, for the first line it is 1 2 3. For the first column it is 1 1. At this position, this sum 1 plus 1 minus 0. 0 is added twice, plus 1. So what is this? This is 3. 3, and this is 4, this is 5. 4 5 6 7, not 4 5. 3 plus 2. 3 plus 2 minus 1 plus 1. 5. And the next at this position, at this places, 5 plus 3 minus 2 plus 1, 7. And you can also see that 3 plus 4, 7 is there. Okay, now let me apply the same formula and get the prefix sum. At this position, this sum plus this sum, which is 4, minus this sum, minus 1, plus actual value at this position, plus 1, that is 4. So for this position, let me remove this portion. It means sum of this section, this position, sum of this section, 5 plus 4, minus this portion which is included twice, this is 3 minus 3, plus the actual value at this 1, 5 and 5, 1, and this is 7. After that, 7 plus 7 plus 1 minus 5, 7, 7, 14 and 15 minus 5, which is 10. So this is the prefix sum. This is how I will calculate the prefix sum using this formula. So what we did is, we had the grid, we took the prefix sum, and using the prefix sum, we can find out how many square we are forming at every single position. Which is the biggest square I can form at this position? That is 0. Which is the biggest square I can form at this position? One size square I can form. Two size square, how do I get to know two size square I can form? Two size square I can form if I check that whether this portion is giving me sum equal to 4. So to check whether this portion is giving me sum equal to 4 is, what is the sum so far at this position? That is 5. Here above it, no portion is there. Left side it, this is the portion. So left side portion is giving sum which is 1. So 5 minus 1, which is 4. See, this is something I did. So at any position, let's say I'm checking for a simpler case. What is the biggest square I can form using 5? That is something like this. One size I can form, definitely one size. How do I get to know? 5 minus 3 minus 2 plus 1. What is that? That is 1. One size square. To form one size square, I require area to be equal to 1, which is equal to 1 into 1. Fine. So now check for the two size square. For two size square, I should have area which is equal to 4. So 10 minus this 4 minus this 3 plus this 1. So what is the value? 4, 5, 6, 7. So 11 minus 7, which is 4. This portion, it means this portion is having size equal to 4. So yes, if size is equal to 4, it means all the items are 1. This is something I was able to apply because all the items are either 0 or 1. So that's why I applied prefix sum, and that was all about my prefix sum approach. I will also attach the code in the description below. Still, if you get some doubt, you do ask me. Now let's come to the typical standard way of doing it using dynamic programming. What is this dynamic programming? Dynamic programming means whatever problem we are given, we have a subproblem where that subproblem is of the same nature of problem, and there are overlapping subproblem as well. So which we can memorize using some DP table, using some caching or anything. That is typical form of our top-down DP approach. Okay, so to move to that top-down DP approach, there is one prerequisite question. You should not directly jump to this one. There is one prerequisite question which is maximal square. Maximum square. So guys, so far I hope that is clear that using prefix sum we solve that question, but that is order of n cube. Though it is getting submitted on LeetCode, but still you can try this DP approach as well. Now the second approach, we are coming to DP, where I am telling you some prerequisite question. Prerequisite question is 2 to 1, and this 2 to 1 is saying that in this grid of m cross n size, where items are either 0 or 1, find the largest square containing all ones. Largest square containing all one. Square means both the side should be same. So this is my prerequisite question. And in this prerequisite question, what I can do is, let's say I have to find out all the square, biggest square ending at 1. Biggest square ending at 1. What we will do is, we will check for biggest square ending at every single one. Every single one, correct? So let's say if I check biggest square ending at this one, so how do I get to know? If let's say there is one block and which is equal to 1. So I want to know what is the biggest square ending at 1. So I can say that what is the biggest square ending at this block, and what is the biggest square ending at this block. What is the biggest square ending at this block? Take the minimum part and add 1. Whatever is the minimum part, add 1. If let's say this is 0, so it means 0 square is ending at this position. If it is 1, it means one size square is ending at this position. See, why I'm saying so? Because to be equal to this, it means it should be a part of this form. Let's say this is the biggest form this is the biggest square I can form using this block. It means this portion should be 1 and this portion should be 1, and all the items in this portion should also be 1. So if this portion is 1, so let's say this is the case. This square is equal to 1 if this is 1. And if that is 1, this square is equal to 1. But let's say this middle square is not that sufficient. It is equal to like this. So we won't be able to capture this portion. It means whatever is on the left side, whatever is on the top side and diagonally top side and left side, whatever is the biggest square I can form ending at these 3 positions, take the minimum one, and that will get expanded to include that one. This is like the crux I am telling you about the problem statement. You have to go to this problem statement, read about it, and to understand why I'm saying so. So let me take the same example. 0, 0, 1, 1, 1, 1, 1, 1, 1, and 0, 1, 1. This was the question for us. And here, what I want to know in my given problem, I want to know all the squares with all 1. But I told you a prerequisite that is maximal square. What is the maximum square I can form ending at any position? Ending at any position. Let's say ending at this position, what is the biggest square I can form? Or let's not consider this. Let's say this is the square. At this position, what is the biggest square I can form? It means that this is a kind of portion here. To form a biggest square, it should be in this form where all the items are 1. Here at the left side, it is 0. It means definitely I cannot form anything. I cannot form a square. So there is no sense on taking checking for the other values. So if it was something like this, instead of 0, if it was 1, I was having 1 on the left side. Okay, there is some scope. Or 1 on the right, 1 on the upper side, 1 on the upper side. I can form a square of size 2. Correct? This is something highly intuitive. You need to understand that, okay, at this position, what is the biggest square? Biggest square is this. At this position, biggest square is this. At this position, biggest square is this. So what is the biggest square at this? The biggest square should be this one. I'm drawing with blue line. So that will be the minimum of above one, left top, and the left side one. So if I directly talk about the dp of I and j, I need to know at every single position what is the biggest square I can form at this position. That will be equal to 1 plus. So whatever is the square, biggest square on these three portions, minimum of dp of I minus 1, j minus 1, this left portion, and dp of I minus 1 and j. Now dp of I and j minus 1. So whatever is the minimum of these three, this one and this one, minimum of these three plus 1, because whatever is the square that will be expanded to one more side. Let's say this is the square and this square need to be expanded to one more time. It means that let's say this square is of size 2. There should be at least 2 size value at this position, at least 2 side value at this position, and this is already 1. So definitely we have to choose minimum. Okay. So this is the equation I can form, and this equation is going to give me the maximum square at every single position. If the maximum square I can get at this position is 2, it means I can add 2 to my answer. So here, if I check the maximum square at every single position, if this one is having maximum square equal to 2, it means it can also have a square of size 1, it can also have a square of size 2, correct? So whatever is the maximum size square, that can directly come to my answer. That is like number of squares filled with 1. So my problem statement is whatever we did in the maximum square. My current problem statement is that find the largest square I can form at every single position, ending at every single position. Given m cross n matrix 1s and 0, how many squares and matrices I can form where all the items are 1? Okay, this is the problem statement, and now this is the final time I am discussing it, because we have the formula. Now in terms of dp, what I will try to figure out is at every single position, what is the biggest size square ending at this position, plus what is the biggest size square ending at this position, plus what is the biggest size square ending at this position. At every single position, whatever is the biggest size square you can form, just that is directly added to the answer. So my answer is 0 initially, and then I will go row by row and I will check for the maximum square ending at every single position, and that I can form. Let's say I'm choosing this ij, and let's say I'm taking a tabulation, taking a dp table of same size which is m cross n. Then how do I fill the dp? What is the maximum square ending at I and j? That is equal to minimum of maximum square ending at this position, maximum square ending at this position, maximum square ending at this position. So that is minimum of maximum square ending at I, j minus 1, I minus 1 and j, and I minus 1 and j minus 1. Minimum value plus 1, because current value is also 1. If the current value is 0, then there is no sense of applying this formula. So just apply this formula on every single position, and whatever is the value here you are getting, that will be added to your answer. Answer plus equal to dp of ij. Correct? So this formula we can apply. Now let me help you with a dry run over this formula. 0, 111, 4 times 1, this is the dp. This is the given matrix. And what about the dp? What is the first row? 0. For first row, I don't have to apply or use my brain, because first row means the square size will be at max 1. So if it is 1, add to the answer, add to the answer, add to the answer. So the answer is 3 now. Answer was initially 0, then 1, then 2, then 3. Answer is 4 now, and it is 0. At this position, minimum of this, that is 0 plus 1. So 1 is the maximum size square I can use at this position. That is also added to the answer. Now at this position, 1, 1, 1. Minimum is 1 plus 1, that is 2. So 2 is added to the answer. So 4 and then 5, then 7. 7 is the answer. Now 2 is here. Minimum is 1 plus 1, that is 2. 2. 7 and 9. At this position, 0 plus 1, 1. This is 10. And at this position, minimum is 1 plus 1, that is 2. It is 12. Minimum is 2 plus 1, which is 3. 3 is the maximum size square. So 3 will also be added to the answer. 12 plus 3, 15. So 15 should be the answer for this problem. So this formula is giving me the correct answer, and yeah, we can directly use this bottom up approach, where I directly filled my tabulation table, where I went from the smallest problem to the biggest problem, and covering that every single position, I need to know the number maximum square I can form at that position. That will directly be added to my answer. So what I did is I took a DP of m cross n table. You can also take m cross m plus 1 n cross n plus 1. That does not make sense, because first row I am sure that it is the same. First column is the same, and the rest of the grid will be filled using this formula. Minimum of this value, and this value plus 1. So that is my answer. And here we are able to solve it in order of m into n time. Earlier using prefix sum, it was taking order of n cube time. So it's a square quadratic solution, and that is going to be submitted. And let's have a look on the code now. So here, first of all, let me show you a snippet of my prefix sum approach. So what I did is, in this is my prefix sum, the formula for my prefix sum in 2D matrix, and this is something which is very important. Let me see, in the similar question they have said something or not. Let me open it in the next tab. Range sum query 2D immutable. Range sum query 2D immutable. You can solve this question if you want to go with that prefix sum approach. Solve this question first and try to get on this one. And if not with the prefix sum, so I checked for the prefix sum, and for every single position ij, I checked what is the maximum size square I can form. And here I took benefit of that portion, like from ij left top to i1 j1 right bottom. I check for the formula where I'm going to get the sum of that particular matrix, sum matrix. If that sum is equal to a square, it means that it is a square, and we can count that in my answer. Starting from ij, can I form a square of size 1? Can I form a square of size 2? Can I form a square of size 3? Can I form a square of maximum possibility I can make? So this is something I did. And now this was the second approach. Second approach is pretty straightforward, kept it very simple, brute force manner, not brute force, bottom up manner, the typical bottom up manner on 2D matrices. And before that, you can solve a question. There is a question on DP study plan. In the DP study plan, if you just open it, DP study plan, Fibonacci style, matrix style. In the matrix style, there's question maximal square. Try to figure out that question first. Maximal square. It is the same question, that if I want to get the sum at this position, minimum of left top one and top one plus 1. This is the sum. I can format this position. The same formula I have used here in my approach as well. Where is my code? This is my approach, and the approach exactly is what is the maximum square ending at ij. What is the maximum square where top bottom of the square is ending at ij? So what is the size of the square? That is the answer. Total plus equal to dp of ij, whatever is the dp of ij. Okay, this was not pretty straightforward, and there was a lot of prerequisites. If you want to go with the dp stuff, that maximal square you try first, and still if you are not able to digest or understand, do have a discussion in the Discord community.